which are
A state-of-art approach for point cloud registration that is titled teaser, which stands for truncated least square estimation and semi-definite relaxation. It outperforms all previous approaches in speed and accuracy. There is no any doubt in that. Just note the term certifiable. We will come to this at last. This paper is from MIT Spark Lab and is published in TRO 2020 issue. Pose, like posing for a selfie, means orientations. The authors try to solve the 3D-point cloud registration problem is a simultaneous pose finding and correspondence finding SPC problem. Note this term SPC also. We will also need it at last. Remember, point cloud algorithms solves an optimization problem like shown here that gives us three things. Scale, that is applied to the model with respect to the scene. Translation in RQ, that means normal Euclidean space. Rotation in SO3, SO means special orthogonal, that represents all rotation about origin in Euclidean space. Remaining in this jargon is 1 by beta square, which is just to normalize the error on each point. Beta is also called noise bound. Remember, we want to find three transformations: scale S, rotation R, and translation T, that maps feature of this red rabbit, for example, to features of this blue rabbit seen to model. This is what we have been doing in ICP2. In ICP, we had assumed that the nearest point was correspondence and iterated. Life was far easier there. But even with more correspondence and robust feature detectors, over 95% of the generated correspondence can be incorrect in practice. So the magic sauce is that we first decompose the entire estimation problem into three sub-problems: scale estimation, rotation estimation, and translation estimation. Look at this cool animation showing decompose three problems. We will surely talk about decomposing later on. And after decomposing, we use truncated least square cost function to solve each of the sub-problem. We are all familiar with similar variants of least square. If you remember robust least square in Ranjak, focus on this image on the right. We have our normal least square within this noise bound beta. Also, normal least square cost curve is shown faintly outside this bound for comparison. If there is some residual that is bigger than bounds beta, truncated least square will give a fixed cost, right? So the obvious benefit of these are for outlier or first correspondence, it won't generate very large cost like in normal least square. In Euclidean space, there are some invariant measurements which consist of values that are invariant under different measurement. The first insight is the relative positions between points are invariant in translation. For example, say if you have a ruler or scale, so you point it northward and you translate it up and down, left and right, front and back. How much effort you put, the length of the ruler and the initial direction pointed by the ruler is not going to change. This is the beauty of Euclidean space. So the relative positions or vectors are not affected by translation. So they are also called translation invariant measurement, TIM. Look at this TIM equation. It doesn't have T. Everything is familiar except OIJ and EIJ. OIJ is 0 for inlier and arbitrary number for outlier. EIJ is just measurement noise. Another insight is that norm or relative position or distance, whatever you say, between each pair of points are invariant against translation and rotation. You can imagine randomly translating and rotating a football anyhow you like in any direction. However you do, football size is not going to expand or shrink, right? So norm or size or scale, they are not affected by translation and rotation. So they are called translation and rotation invariant measurement, TRIM. Look at this TRIM equation. This is same like one we saw before. If you divide this by AIJ on both sides, you get SIJ. SIJ is measured scale from this sphere. And S is the global scale value that we want to estimate here. This is a very summarized pipeline showing the teaser algorithm. So basically, we first estimate the scale using adaptive botting, and then we estimate rotation using semi-definite relaxation, which is very complex and slow in practice. We will also introduce another blazingly fast way to estimate rotation in milliseconds using GNC TLS, which authors have called teaser++. And finally, we use adaptive botting again to estimate the translation. This is the first step. We are estimating scale yes using translation and rotation invariant measurement, TRIM. Focus on the same modified TLS equation that doesn't have R and T. Argument is argument of the minimum. We all know that. For simplicity, we have numbered the invariant measurement from 1 to K and adopted the notation SK instead of SIJ in previous slide. Here, K is the number of pairs of correspondence point which scale is being considered. C is set to 1 by authors. See the minimum part inside this summation. The equation discards outlier measurement with residual greater than C square, that is 1. Look at the square term inside this bracket. This is cost or error. If this ratio is greater than 1, it is discarded by this mean function as a constant cost. Remember, this is TLS. After that, they use botting algorithm that we have seen before, right? To solve the TLS problem exactly and in polynomial time. You can visualize the whole process here. Distance of pairs I and j from both models seen and both model and seen. This is Aij and Bij are used to calculate for Sij. We had called it Sk for simplicity in last slide. This is adaptive voting. There is adaptive voting done among such Sks or Sijs. Has been with the highest vote among such Sks is chosen as the optimal scale value S and is guaranteed as the optimal solution. Finally, we have optimal value for S. Now, we need to find a way to solve second suboptimal problem, that is rotation estimation. The equation looks almost similar as before, but this is TIM. Before it was TRIM. So you can see R here. Other notation seems familiar. Delta square seems new, but the meaning is same as alpha. Error bounds for TLS. B is seen. S is scale. We just found. R is rotation we are hunting for, and A is model. We can't think of adaptive voting here. Why? Because remember R is a rotational matrix. Its size is 3 by 3. If rotation was a scalar value, there was no problem. But R also has a pitch and row component inside. But we can solve it as a QCQP. Quadratically constant quadratic program. It is an optimization program in which both objective function and constant are quadratics. We introduce new notations. There is some typo, but this is A hat and B hat. A hat incorporates scale S and A bar, which is model features. Likewise, B hat incorporates B bar, which is scene features. Let's not talk about dimensions now. This equation are copied as it is from papers written by top researchers from MIT, so we can trust him, right? So just leave that dimensions for now. Focus on the term that looks new for us, Q. This is Quaternion. No need to get scared by name. Remember, it is a 4D representation of rotation. Look at this unity sphere. It can be used to represent any 3D rotation with 4 parameters. Across this 3D vector, x, y, z, you can rotate this unity sphere by angle theta. So rotation by theta is the new component added to this 3D vector to make it 4D, to represent rotation. This is one way of explaining Quaternion. Q can also be explained as component of 4D unit Quaternion, like sum of squares of component of unit vector is 1. Sum of component of Quaternion is also 1. Unit Quaternion is also 1. We will use this property later on, just keep in your mind. The small O-like notation is Quaternion product. This is non-commutative, so for simplicity, we'll just think it as a vector class product and move on. The advantage here is that we have transformed our matrix in SO3 to a 4D unit sphere with Quaternion. Closely look at this top equation. We have seen similar idea in cost function of logistic regression, if you remember. Try putting theta barabar 1. This will, you will get x from here. Try putting theta barabar -1, you will get y. So there are two possibilities of this term, x or y. There is also a mean from here. The beauty of this equation is that it returns x or y, whichever is minimum. With these intuitions, we are rewriting our TLS problem as this. No magic is done here, just focus here. Theta k seems new. Almost other things are similar. Theta k is new here. But we know what it is. It can be either +1 or -1. Also note that when theta is +1, the first part of equation is chosen, this part. And when theta is -1, the second part is chosen. Or the correspondence is treated as outlier. That is the meaning. So we are doing the same from TLS, if you remember. Our ultimate goal now is to solve for single rotation that is transformed as Quaternion here, and k number of indicators is theta k. That is +1 for inlier and -1 for outlier. You can imagine the situation is every point relying on the same rotation with varying motion distributions. This is actually very non-convex and hard to solve. To reformulate, we are duplicating the Quaternion k times, multiplying q by theta. That means we just multiply these terms. So we will have k numbers of qk's here. You can see k number due to summation. Here is summation. Now you can imagine every point now rotates by itself with its own qk. The benefit is this equation looks more convex than equation at top. Again, for qk plus qk, this will return the first part of the equation, and for minus qk the last part, or say reject as outlier, same like TLS. Remember, in this situation now, we need to solve for k plus 1 values, 1 q and k number of qk's. Here we are rewriting the quadratic functions to be minimized in quadratic constant. X is introduced as a column vector containing unknowns q and q number of qk's. Q is non-symmetric matrix that contains the TIO measurement of A and B, model and scene. Again, let's trust MIT guys for dimension and move on. Now minimizing this scary function above is equal to minimizing x transpose qx. How? Because all terms here are incorporated inside x and q. Actually, this is kind of a rewrite. Yet this function is still non-convex due to these constraints. Check this first constant. X q transpose x q barabar 1. This is a quadratic equality constant which have distinct feasible points. Sadly, they are also non-convex. X q is a 40 subvector of x column n has single q only inside. So this constant is actually equivalent to q transpose q. Remember, q has component of unit quaternion inside. So q transpose q is the sum of square of unit quaternion. This is 1, like I said before, if you remember. So xqk is a 40 subvector that contains qk. Qk times qk is a 4x4 matrix. This is it. So just note that q times q transpose is like 4x4 matrix. This it contains the square subcomponent of unit quaternion in the diagonal. So you can just realize this. If you multiply like this, it will like the square will come in the diagonal, right? So, and just look at this term q k and qk transpose. So qk is equivalent to theta q. We know that, and there are 2 theta. It will be theta square. Right? Theta k either positive or negative, this square is always 1. So this is trivial. These two are equal. So these constants are justified. Look here, TR is trace. This is equal by Borgia of matrix algebra. This is this and like this is equal to this by Borgia matrix algebra. So let's not discuss it more. So we suppose z barabar x transpose. The function will change to transpose trace of qz. This is also just a kind of rewrite. Look at what is z. Z, we just let it like x transpose. So x was a column vector of q, the quaternions. Remember, the element of z is now positive semi-definite matrix. How? Because any matrix in the form x transpose is a positive semi-definite rank 1 matrix. Vector algebra says that, not me. Its eigenvalue are non-negative, strictly positive. So here is plus sign. Now look at the modified constant. Trace of z00. What is z00? This one. This is the sum of element of the main diagonal of matrix. This will give the sum of square of component of unit quaternion here, if you remember from last slide. So this is 1, there is no doubt. Now look the second question. Remember theta square in last slide. That also means every diagonal entry of z will be equal to 0, same as before. So this all will be equal to z, q transpose here. You can see this term. So here will come theta 1 and theta 1. So theta 1 square will be equal to, it will be same as like this. Now look at the third constant, rank of z. Z is x transpose. Remember what is x again? Column vector with k and qk's. Z has rank 1. How? With just one independent term q. All qk's are dependent on q. So from total rank theorem, we can say z also has rank 1. Just as a side note, all previous constants are preserved here. Nothing is new. This is just conversion due to like new variable z. But relaxing is still not done. That is what we were going to do, right? So the only relaxation here is that we drop this rank z barabar 1 constant. We don't require z to be exactly matching an existing x. That is, it should not be satisfied. Instead, we only require it to be symmetric for making it convex. That is the goal. If we somehow find q and qk's, that's enough for us. So top two constant are same. Photocopy it from here. Focus on the new constant. Remember transpose property. This third redundant constant enforces all the off-diagonal element of z to be symmetric. Please note this term at last. Off-diagonal elements are in fact signed copies of QQ transpose with additional theta as envelope to tag either as inlier or outlier that we were referring as QK before. This relaxation made this in exactly convex problem. We can now guarantee that a global optimum is achieved with those relaxed constraints. However, a global optimum of the original problem still cannot be guaranteed. Only of the relaxed case is guaranteed. So we optimize theta and theta case from. We optimize q and theta case. That is what we are doing, right? Theta case and q from this convex problem and obtain both rotation and correspondence. Q will give pose or rotation. Theta case will give correspondence. Hence, justifying this method as a simultaneous pose and correspondence SPC approach, which I mentioned in my first slide. SPC. Remember that. फेरि यहाँसम्म आइपुग्दा के गरे नि बिर्सिनु भयो होला. यहाँ चाहिँ हामीले आर निकालेको थियो. यो विशेषले अहिले यो आर चाहिन्छ, नत्र उहाँको त्यहाँ इक्वेसन सल्भ हुन्न. ठिकै छ. Look at this beautiful picture. Right? This shows how relaxation we did now can transform this non-optimal TLS problem to a STV problem that can be solved exactly in polynomial time. But although this is better than existing algorithm and give exact solution, unfortunately, like you might have already guessed, this way of using semi-definite relaxation is pretty slow in practice and requires extensive computations. So they propose to change the second sub-problem, that is rotation estimation, with another novel approach called GNC TLS, which is basically an iterative method that uses truncated least square cost function to achieve pretty robust estimation of rotation in milliseconds. See that? So the first GNC TLS is a method to solve for rotation. Remember, we want to make it as convex as possible, but it should be able to separate inliers and outliers like truncated least square. our favorite one, this least square, it is ideally convex, but they are not robust to outliers. We all know that, right? So just remember, mu is a parameter that controls convexity here. So if you slowly increase mu, it will make this orbit constant, just like this. And also, it will be somehow robust to outlier. So we want to find an optimal condition for mu, for which the first function is both convex enough to solve and is robust enough towards outlier. There won't be exact solution of this, of course, right? So we need to gradually iterate from simple surrogate, what is surrogate, like cost functions like least square, convex cost functions, and we should gradually increase the convexity, gradually decrease the convexity and try to make it more robust like TLS. That is why it is called graduated non-convexity. This is the main idea behind GNC TLS. So you probably remember the word certifiable I mentioned before, right? Let's talk about that now. Focus on this figure. The cone in green hyperplane shown here is formed by projection of positive semi-definite matrix Q in Z that contains the rotation quaternions. Now we won't get into more math. This is also boring already, right? So the main idea is that we get first heuristics from GNC TLS and use the knowledge of SDP problem to give a certificate on how good or how close this solution is to the global optimum. You can always Google teaser and learn in details if you are interested. Thank you for tolerating me. I need to breathe now. So BCC will continue from here.
Now, since almost all the mathematics have been taken care of, now I think we've got what it takes to calculate the translation. So, since we have decoupled the main task into 3 sub-problems, after obtaining the scale and rotation estimates, we can substitute them back into the original truncated least squares formulation to estimate the component-wise translation T1, T2, and T3 independently. Just like scaling, the translation is also estimated using adaptive voting, which Sushant sir discussed earlier, which gives us the number of invariant measurements. Having known the scale and rotation, the x, y, and z components of translation can therefore be separately estimated from the model and seen. Now, there are a number of approaches for robot registration of the acquired point clouds. RANSAC is one of the most popular frameworks using random or non-deterministic approach. It is robust against outliers as it separates the data points into a set of inliers and outliers. However, RANSAC requires a minimum solver which is not available for several problems in perception. Also, the number of iterations in RANSAC grows exponentially with the increase in outlier rate as well as the increase in number of sample points. That makes RANSAC inefficient in higher level of outlier regime, making it not suitable for real-time applications. It is not really very effective in estimating multiple fits too, as the number of required sample points increases with the number of multiple lines involved and of course multiple hypotheses. Therefore, RANSAC fails with a large amount of noise and a high percentage of outliers, such as over 95%. So another approach called M estimators fail at over 70% of outliers, whereas the guaranteed outlier removal GORE is robust against over 95% of outliers, but just like in RANSAC, the time required for registration process increases exponentially with the increase in outlier rates in GORE also. The given plot compares the performance of teaser and teaser++ with different algorithms over some simulated dataset from an image of a bunny. The rotation error is plotted against the outlier rate from 95 to 99%. RANSAC is tested among its 2 variants. One, a fast version RANSAC 10K, which terminates after a maximum of 10,000 iterations, and a slow version which terminates after 60 seconds. RANSAC 10K and fast global registration FGR perform poorly under outlier rates above 95%, giving large rotation errors nearly up to 100 degrees, whereas RANSAC 1 minute with 60 seconds of timeout can resist up to 98% of outliers with about 10 to the power 6 iterations, maintaining the rotation error only up to a few degrees. GORE, however, stays robust up to 99% of outliers, and teaser stays correct, robust, and accurate from no outliers up to the 95 to 99% rate of outliers and runs in polynomial time, making it faster among other approaches. The experimental setup has used 3D mass dataset which consists of RGBD scans of 62 real-world indoor scenes. with 5,000 randomly sampled key points for each scan. The blue lines over here in the image indicate the original correspondences with outliers obtained from feature matching. The green lines signify the in-layer correspondences computed by teaser, and the registration results from teaser highlighted in red imply a successful localization and pose estimation of the object. This illustrates that teaser produces accurate results with very low rotation and translation errors at high outlier rates, giving a robust performance. Now, as we already know, the process of 3D registration that we have been discussing about all along has a variety of approaches, and it involves alignment of 3D scans and then registration estimation using those scans.